Hi everybody, today we'll be talking to you about medical coding using machine learning. My name is Samuel and Opanin. I'm part of the fellows for the Ishango Fellowship Program for the year 2022 here in Ghana. I have a bachelor's in mechanical engineering with some experience in the drone industry. I've developed interest in deep learning and then natural language processing.
Hi, my name is Opanin. I'm also one of the Ishango fellows for the year 2022. I have an MPhil in applied mathematics. I'm hugely interested in research that focuses on finding smart solutions to real life problems using deep learning techniques. So this is the outline of our presentation. So I'm going to take you through the first two chapters where I present the problem, the data involved, and my colleague will talk you through the solutions we implemented, the results we have to show for, and the impact of these results. So in the mid 20th century, pregnant women did take a drug called thalidomide to help curb nausea. So this resulted in a lot of deformities in the babies. As a result, who actually established the whole science called pharmacovigilance to help curb this situation. So the company that we work for, Phastar, is a major stakeholder in the promotion of pharmacovigilance, where they act as a specialist biometric contract research organization, giving clinical trial reporting, statistical reporting, data management solutions to pharmaceutical companies. So the problem that we are trying to solve is on clinical trial reporting, where adverse effects from clinical trials have to be documented. So, in the process or the event of clinical trials, the adverse effect that individuals who partake in clinical trials have to be recorded at the site. So they go to the site and record the adverse effect that they are experiencing. So this data is then passed on to a data manager who has to actually push this term to or match this term to a more standardized terminology provided in the Medra dictionary. It is very cumbersome doing all this process, so they try to automate this process using an autocoder, which has been found to be 60% efficient. So after this hassle, a specialist has to confirm whether the data manager was able to properly code this adverse event to the proper terminology in the Medra dictionary. So in order to improve on the 60% benchmark of the autocoder, we realized this set of problems of the autocoder. First, the autocoder cannot only does direct matching. So it cannot see the difference between vomiting and vomited 4 times. It will always see them as two different terminologies and will not be able to match vomited 4 times to a corresponding ALT. The autocoder also doesn't understand semantics. So when you have a word called vomiting, which might mean the same as puke, the autocoder will not be able to differentiate this. And also when there's a spelling mistake in each of the verbatims, the autocoder wouldn't find a way to work around it. So we decided to build on the autocoder from this perspective. With that in mind, we devised this methodology where we retrieve the verbatim terms or the adverse events. Then we pre-process these terms, search in the Medra dictionary for the right terms, and present the data manager with a set of LTs a set of terminologies that they can select an appropriate one from. So these are the tools that we used. We use Python, NumPy, and sklearn. And for our text processing, we used the natural language toolkit. And for our semantic understanding, we used SBET.
Okay, so we went on to try to improve on the exact matching method as part of our techniques to solve the problem. So we did some exact matching, do some pre-processing to try and improve the exact matching between a verbatim term and then the standardized term that is known as the LLT or the lowest level term. And then in situations where the exact matching doesn't work, we use a more similar a method that tries to find similarity between two terms or two medical terms or two verbatim terms, a verbatim and an LLT term, by using the words that is find similar between them. So in the end, word frequencies. And then we try a more better method that tries to understand the semantic meaning of words or terms, so that we use that to be able to code any particular verbatim term given to its corresponding LLTs using the semantic meaning of terms. So you can see in this example over here that vomiting codes directly to an LLT vomiting, but then intense vomiting is unable to code to vomiting when we are using the exact matching method. Why? Because then it doesn't. Those two are not exactly the same. So then we are in trying to improve the exact matching. We did some preprocessing steps, cleaning, stemming, which reduces the base form, and try to order the terms inside to just improve the accuracy. And we realized that we were only able to improve the accuracy to about 85%. But then there are more scenarios where exact matching doesn't help. And then this is where word frequencies come in. Word frequencies uses words that are the same or similar in both words and try to determine some similarity between these terms. So we can see that vomiting and positive vomiting for word frequency or the TF-IDF in this case is finding some similarity between them. But then we realize that the SBET is able to find more similarity or a higher similarity because then it sees or it's able to calculate the semantic meaning or determine a much higher semantic meaning or semantic similarity between the two terms. And it is more prevalent when you use verbatim and when you use a verbatim vomiting and then an LLT stomach flu, you realize that with the word frequencies. Now, it's not finding any similarity, but then our model or the SBET model is more able to understand the semantic meaning between these terms, and it can code a verbatim term vomiting to an LLT term stomach flu. So then we apply these two models to try to code the verbatim terms in our data of about 5,000 verbatim terms to the Medra dictionary, and then in the end, when we let the model suggest to us the top 10 terms that are more similar to any verbatim term, we realize that we're able to code 92% of the verbatim terms that were provided to us or that were given to us. So in the end, with using the SBET model or using the sentence transformers model, which understands more semantic meaning between terms, and then allowing the model to suggest to us the top 10 terms that are more similar to any verbatim term, we're able to code about 92% of the terms, which is a huge improvement on the initial 60% that the autocoder was doing. Now, how does this improve the whole process? We realize that we're able to reduce the coding time for any particular coding. The time is drastically reduced, the resources that are used is reduced, and then the review time, the time to review or the codes is also reduced, and it's just improves the whole overall efficiency. And this model can even be applied in situations other than clinical trials, where terms have to be coded to a particular standardized form. Thank you.